Okay, hello everyone. Welcome back to another webinar by Rated Power. And while we are waiting for everyone to join, we're just going to wait 1 or 2 minutes for everyone to download the application and join the webinar. I just wanted to remind you everyone that we have access to a lot of information. You will be able to access all the previous webinars from Rated Power in our YouTube channel. Everything is for free. There's a lot of useful information regarding how to use PV design, regarding in general topics about Rated Power software, about how to design PV plants. We have a lot of experts and people with knowledge in the field. And you will also be able to find a lot of resources and information in Rated Power's page, some ebooks and reports, uh, webinars that will be launched in the future. This one, the third one, is the one that we are going to be hosting today. The one in the middle, I don't really know what is it about. So you will be able to have a lot of access to very useful information. So now let's wait just a couple of seconds for more people to join, and we will jump directly into today's topic. So today's webinar is going to be about grid integration studies. Many times we forget about the importance of integrating our PV project into the grid and the challenges that this poses. And this webinar tries to aim at this stage of the PV project. So without further ado, let's begin. So first, a bit of myself. I'm Alvaro Benito. I'm a software developer at RatedPower. Joined the company 3 years ago. I've been working in the electrical part of interconnection applications, overhead lines, substations, and power flow model. And I'm really passionate about engineering, specifically electrical engineering. So I'm really happy to be showing you the knowledge that I've acquired for the last years. And this webinar will be divided into 6 sections. First, a brief introduction. I don't want to spend too much time on that, in which I will showcase what will be learned during the webinar. Then we will move on to inverter sizing, also to capacitor banks. Then we will do a brief analysis on power flow, not going deep into the mathematical aspects. And finally, some rated power real use cases and a Q&A session. So jumping into the introduction, these are basically the objectives of this webinar. Today, I would like you to understand a bit on equipment sizing. How do we define the number of inverters that we're going to be placing in the PV plant? How do we know whether we are fulfilling the requirements of the TSO and other grid requirements, and whether we need to add more or less inverters? We're going to be covering capacitor banks, how to size them, when to use them, or when to use more inverters. Then for power flow analysis, we're going to understand how to model a PV plant. So once we have the entire design, how we can translate this into an electrical model so that we can run power flow analysis. And then we will do a brief introduction of power flow calculation. And finally, I would like you to understand how you can use rated power to streamline this process by helping out with the inverter sizing, taking into account a power factor. So this is a bit of the introduction of the presentation. And now let's just jump directly into the inverter sizing. So inverters are these elements in the PV plant that transform the DC power into the AC power. They are highly complex power electronic systems. And just to understand a bit of their behavior, some key takeaways that are going to be needed towards their sizing. We have here an example of a curve from a Huawei string inverter. And there are like 3 main important things that many times are not considered. First one is that the apparent power depends on the voltage. So the higher the voltage that the system is working at, the higher power we can obtain from it. As you can see, the red curve that represents a higher voltage of 1 per unit can go up to 105 kilowatts. When we have only 0.9 voltage per unit, we can only reach 100 kVA kilowatts. Sorry. So this is something very important. Another thing to consider is that they have a limited reactive capability. So you will not be able to inject or absorb as much capacity as you want. In this case, this is limited to 63 kVArs. And finally, there's a limit in the voltage range. So we cannot surpass certain voltage and we cannot go under certain voltage. And this will be important later when we size everything else. So now, what is the process towards sizing the inverters? It's a bit tricky because it has a lot of back and forth communication between the design team from the PV perspective and the transmission line teams. There are many times a lot of communication back and forth between different departments, which causes a lot of time consumption. And we can showcase this in this schema. So basically the first step towards the sizing of the inverters is an estimation of how many inverters are we going to be placing. We just know that we have an available area. We just know that we have a specific type of inverter, specific structure, specific module, etc. So we have some rough data of the PV plant, but we don't know anything. We don't know how much can we fit. We don't know what are the cable losses or length. We don't know a lot of stuff. So we have to just design the PV plant with a first estimation of inverters, what we think will be enough to meet the TSO requirements. So we design the PV plant, we run a power flow analysis, and with this power flow analysis, we can understand whether we met this TSO requirement, the transmission system operation requirement. But if we did not meet this requirement, we have to go back and change the plant. So we might have to add more inverters, we might have to add capacitor banks, or if we were not able to work the inverters at a voltage level that is admissible, we might have to add tap changers to the transformers. So PV design focuses a lot in the first estimation of inverters. So we will jump directly into how this can be done. A lot of people do this with a simple Excel file with simple calculation of losses just to give a first estimation, but we can go a bit further and try to give a more detailed estimation. So regarding this first estimation, we have 3 steps. The first one is to get an approximate electrical model. So since we don't know anything, we can try to get an electrical model as close as possible to what we would expect to obtain in the end. Then we have to estimate the losses of the different systems. And based on these losses, we can give this first estimation of number of inverters. So for the electrical model, we have 3 challenges. First one is the cable modeling. Again, we don't know the routing of the cables. So how do we know what cables do we use? The second challenge is the capacity estimation because we just have a piece of land. So we don't know how many megawatts can we fit there. And the third challenge is the electrical topology. We don't even know how are we going to be connecting the power stations between each other. So again, a lot of incognitas and missing data. So what we can do is try to mock and to create fake data that will be close to reality. And for cable modeling, as I said, we are missing the length, section, and number of circuits of the cables. So what we can do is just to define a voltage drop across the cable. This value will be inputted based on engineering experience. So a very experienced engineer will be able to more or less give a very good estimation. Then with this and the data from the transformers, we are able to build the electrical models. Then we also need to give a capacity estimation. Maybe we already know it, because we want a 100 megawatts plant, so we just go with that. But if not, if we're just gonna try to fit as much as possible into the area, we have to know how much available area we have, what is the equipment that we are working with, the type of structure, the modules, the inverters, etc. What is the pitch distance or the distance between the rows of modules and structures? And finally, what is the DC to AC ratio that we will be using for the inverters? And finally, we need to define an electrical topology. And this is the part where we have no clue what is going to happen. So the best approach is to just consider a single line topology in which we will have an equivalent representation for each of the systems. So we will have a PV generator representing the entire PV plant, a power station, a set of MV lines. Here we can have a capacitor bank or a shunt, a power transformer, and an overhead line. So using all this information, the modeling of the different electrical systems, the capacity estimation, and the electrical topology, we can give a more precise and a more accurate number of inverters to meet the transmission system operator requirements. So this might improve the quality of the first solution, improving therefore the process of going back and forth with the interconnection team that will study the TSO requirements. So then we have to design the PV plant. We already gave a first estimation of the inverters. It was really good, but we have to jump into designing the PV plant. And for this, I'm not going to go into how to do this. You have a lot of information in previous webinars and in the methodologies, which are for free. So I won't be covering this. You just design the PV plant, place everything in the landscape, and you go to running the power flow. I'm going to jump directly into the transmission system operator requirements and then go back to the power flow later. Basically, power flow is a tool that will help us obtain our PQ capabilities of the entire PV plant based on the electrical equipment and electrical model that we have been using. So light going down, okay. So we have to check if these requirements are met by running power flow analysis. So power flow analysis will give us, this is a result. This is an example of one of these results. So basically in this example, we are working at a certain operating point in the point of interconnection, one voltage, one phase of the voltage, whichever. The blue line will represent the capability of our inverters. So it's similar to the curve that you saw from the inverter at the beginning. We see like two vertical lines and a like an arc at the top. And the orange line represents the capabilities of the plant at the point of interconnection or point of common coupling. So this curve will be tilted towards the left. And the reason why this happens is because between the inverters and the point of interconnection, there's a lot of system absorbing reactive capacity. So they are acting as inductive loads. And even if we inject a capacitive or reactive power, part of it will be lost during the path. So in this case, for example, we can obtain a power factor at the point of interconnection of approximately 0.93 and in the inverter, in the inductive part of 0.86. So if our requirement was that we need a power factor of 0.9 all the time, then this will not be met under the condition of injecting reactive power into the grid. Now, jumping into the full requirement, remember this was only under one specific point of operation. This curve is an example that represents all the requirements of all the PQ requirements that the TSO will ask for a PV plant. So we will need to be able to work in the entire blue zone. So we will have to check if our inverters under all their operating points can achieve all the area. And Here there are two examples of just random areas. I just took the shades from PowerPoint to do this, of what would be two wrongly designed PV plants. So in the left side, you can see that the green area represents the operational area that we have from our PV plant, meaning that we can only work within the green zone. In this case, we are not meeting the requirement because there are certain parts of the blue area that are not covered. So we need to add more inverters. But in the second one, you see that we indeed fulfill the entire area, but maybe we can be a bit more efficient and maybe we can reduce the number of inverters a bit to make the green area match the blue area a bit more. So maybe this solution is also not the best in terms of cost. So we already checked whether we meet the TSO requirements or not. And now, if we don't do it, if we don't meet the TSO requirements, or if we did not meet match an economical design, we will have to go back and update the inverters, add capacitor banks, or add tap changers. There are three different solutions. There are probably more, like adding shunts. But there are like three main solutions to fix this problem. The most common would be to update the number of inverters. Adding capacitor banks is something useful if you need to inject more reactive power. And adding tap changers is especially useful if, for example, your inverters are going to be working outside of their operation point of their nominal conditions. So you can add tap changers to control this voltage. But I won't be covering tap changers in this presentation. So we already checked that we can update the number of inverters, but now we're going to jump a bit into capacitor banks because they are another way to add reactive compensation. And basically their main characteristics is that, well, they provide reactive compensation. They are very good with grid voltage regulation. So if there's a voltage drop suddenly in the grid, you can connect capacitor banks and they will be able to inject reactive capacity into the grid and help with the reactive compensation. And they are also very efficient and simple components. You just have a switch and just connect or disconnect them. So very simple to operate compared to the power electronics of an inverter. And then there's different ways to size them. You can size them like specific MVRs. You can define a percentage of the total MVR that you want, of the total reactive compensation that you want, or you can size them to limit the losses or to compensate for the losses that occur during the systems of the PV plant. This like the last one is the one, the compensating losses strategy is the one followed by RatedPower. As you can see here in this example, you have a blue line between the substation input and the point of interconnection in the grid. And this blue line represents that the capacitor bank will be sized to compensate for the inductive losses generated by the substation and the OHL. So if the substation and OHL produce a loss of 1 megavolt ampere reactive, then our capacitor bank will be sized with 1 megavolt ampere reactive to compensate for these losses. This would be an example of how to use RatedPower to size capacitor banks. Now moving into the fun part, to the power flow. First, well, this is the part that we jumped, the third step, and I would like for you to understand a bit on the purpose of this analysis, why we are performing it, and why not just skip it. The main objective of this analysis is that the transmission system operator needs to have the ability to plan accordingly. So they need operational planning. When we are connecting to the grid, they need to know what capabilities our PV plant has so that they can plan accordingly in case of several edge conditions. So for example, for voltage regulation, voltage is too high or too low, same for the frequency or power factor. So in these cases, they need to know how our PV plant can jump to correct these imbalances in the grid. And especially for PV is very important. First, because of the penetration of PV during the last years. Also because it's an intermittent generator, so it's very hard to work with this. It provides challenges. It poses challenges for voltage and frequency regulation, also for grid congestion and grid resilience. And we also have to consider that many times we are coupling these systems with storage, especially in the last years. So it's another thing to take into consideration. Now, how to run a power flow electrical model once we design the PV plant. First, we have to build the electrical system. We have to create all the impedances, all like everything based on the power stations and the cables, power transformers, etc. So we have to build the electrical system, go inside the math and the electrical part of the university, go back to that. Then we have to define the buses. So the buses will be, let's say, the points where the systems are connected to. So electrical systems will be connected to specific buses. Then we have to build the admittance matrix, which represents the connection between the different electrical systems in the buses. And then we just run a numerical method, which is basically a trial and error calculation where we try a solution, we see how close it got to the real solution, and then we try another one until we converge to a solution. And there are like different numerical methods towards power flow modeling. And after running this numerical method, we will obtain 4 results for each bus. So we will obtain the active power, reactive power, voltage, and phase voltage of every single bus, going from the inverters to the point of interconnection. The most important one is probably the point of interconnection because it's the one that the TSO is asking for, but it's also important to know the values at the inverters, for example, to ensure that they are not working with like not within the voltage range. So we need to ensure that all the equipment is working accordingly at voltage ranges that they can work at. Now, this is an example of a rated power simulation result. This is generated in an Excel file with all the numbers. After automatically designing the PV plant, you will be able to obtain all the electrical systems information. So you have here the substation transformers, overhead lines, MV collector, which represents the MV lines, power stations and generator. And given this tree, let's say this graph describing all the elements, all the electrical systems, you can then move them into a different software such as Dixilent or PSSE to run your power flow analysis. So here you have the systems and the buses numbered to make it a bit easier. And this is all following the WECC guidelines. So it's validated. And once you have this, you can transform also the systems to electrical systems if you want by using T-network models for transformers. So the series impedances will represent the copper losses, and the parallel impedance will represent the magnetization loss or the iron loss. And then for transmission lines, the cable losses will be represented by the series impedance, and then capacitive losses to the ground will be represented by these 2 parallel branches. So once you have the electrical systems, you have to define the buses and the admittance matrix. So we have several types, well, 3 types of buses primarily. First is the slack bus, or the one that we use as the reference, which happens in the point of interconnection, so it's the most important one. And then we have buses, PQ buses, where we know the active and reactive power, and typically used for loads, and PU buses for typically generators, where we know the active power and the voltage level. And then we have to define the admittance matrix, which again represents the connection between the different systems. So for example, Y12 would represent the impedance that happens between system 1 and system 2. bus 1 and bus 2, sorry. So this represents the topology of the electrical model that we have. And then we just run the numerical method. I'm not going to go into how, because there's a lot to them, but basically there are like a few options here. The main three options I would say is Gauss-Seidel, which is a bit slow, not the best solution, but it's very simple to implement. So for something basic, it could be useful. And then we have Newton-Raphson and fast decoupled Newton-Raphson, which are very fast, complex, and accurate. Fast decoupled is a bit faster at the cost of accuracy, so it can be interesting depending on the requirement. And with this, we are able to obtain a static analysis on different operation points. So the same curve that we saw before, we just put like in the point of interconnection, we place, for example, in the left side, 110% voltage, and we check what is the window of operation of our inverters under this condition. We check the area and we obtain the operation of our PV plant for different points at the point of interconnection. Now let's jump into use cases. So we have just a simple 3 cases. So this is a site created in RatedPower. It's in Madrid, near my hometown. So we're gonna just showcase 3 simple cases with different reactive compensation strategies. First of them without reactive compensation, so the old PV plant 10 years ago. We don't care about anything regarding power factor. Second one with a requirement of 0.9 power factor at the point of interconnection, achieved only with inverters. And the third one, the same thing, but we're gonna mix inverters and capacitor banks. So we will also include some capex values. I put here a disclaimer that these values are not real. The inverter will be 20,000 euros per unit, 0.5 megavolt amperes inverter, and then capacitor banks 50 euros per kVR. Again, not real values. I want to stress it out. And we just ran some simulations in RatedPower for this site. And we find out that with no compensation, of course, it's going to be the cheapest option because we don't care about reactive compensation. We just optimize the number of inverters. If we have to compensate for the reactive loss, we get 8 inverters, so 14 more inverters, so increasing the cost. And the most interesting comparison maybe is between the inverter compensation and the inverter plus capacitor bank compensation. In the last column, you can see that we reduced the number of inverters by 7 at the cost of adding the capacitor bank. So in this case, with this capex, the capacitor bank strategy is a bit more expensive. So if there's no other requirement and we just consider this, then the inverter compensation would be the go-to solution. But maybe we get paid extra money for the voltage regulation that the capacitor banks can provide, and it could be better to choose the third solution. And with this, I will jump directly into the Q&A session. So I will be reading your questions. You can place them in the chat. I believe there's a place for them. So yeah, you have here all the information. So I see that there are some questions already. So first one is, do you have the option of capacitor banks, or it can be considered any other equipment such as STATCOMs? So right now we only have capacitor banks. We don't have STATCOMs. It's something that we have considered, but for now we are only focusing on that. But for sure we will note down, because this is an open conversation always, to include more elements for capacitor, for reactive compensation. Okay, so there's another one. Is there the option to define the design temperature? Okay, is there an option to define the design temperature for the power of the inverters? So right now, no, we don't have the option. We have the at 30 degrees and 50 degrees, and I believe we use the 30 degrees one because 50 degrees normally is not realistic in most places. So right now we do not have the option to customize that. Okay, let me see more questions. Uh, how temperature affects the analysis and which temperature should be considered. So again, the temperature considered should depend on the site that you are designing. Higher Can you hear me now? Yeah, it should be working. I'm sorry about this, by the way. Still in mute. It's working finally. Sorry everyone. So yeah, I was saying that yeah, there are two strategies implemented in PV design. You can use only inverters or inverters plus capacitor banks. So capacitor banks will be used for the losses compensation. Also, sorry for the mute. I don't know how much have you missed. Um, okay, next one. Is there an easy way to translate RatedPower's power flow model into PSSE? Okay, so this is a work in progress right now. So the only way that you have as of today is to copy paste the values from the Excel file that we provide and create the electrical topology directly into PSSE in this case. but we are working. We're expecting to work in the following months, like in the following 2 or 3 months, in a Power Flow model export tool feature, in which RatedPower will directly generate a new file that you can import in PSSC or Dixilent or ETAP, I think also. So it will be very easy to integrate both softwares and both solutions. Okay, a lot of questions mixed with the with the mute. Okay, so I think I answered everything. If one of the questions, I don't know. Okay, if one of the questions did not get answered because of the mute, I don't know when I got muted. Just feel free to reach me out or reach anyone from RatedPower out. And I would like to thank you all for being here. Okay, I have another comment. Thanks, Alvaro, for the presentation. It will be good to have a cost comparison with the option of on-load tap changers in the future as well. For the inverter sizing part, could it be done in the short-term goal with only a static perspective? So yeah, on-load tap changers is a really interesting topic for us. Since we are building a power flow calculation right now, it's something that we want to tackle a bit afterwards. So it's not in the short term, like in the following months, but in next year we're expecting to deliver this. So yeah, very good appreciation. Regarding the inverter sizing part, um, we are also planning on doing all the PQ analysis for the inverter sizing. So not only the first estimation, but also like a post-analysis after the simulation is performed, just for you to understand all the, like if the requirements are met. So we will be also working on that. That would be before the unload tab changers. So yeah, very interesting topics overall. Okay, so yeah, I think we are already done. I don't see any more questions or any more comments. So thank you all for coming. Thank you all for attending. And thank you all for the patience of having to deal with the mute. uh, Things that always happens. So yeah, I'm glad to have been able to showcase everything. And goodbye.